In this video, we're going to show yet another proof that there are an infinite number of primes, always by contradiction. Assume otherwise. Assume that there are only finitely many primes, namely P1 through Pn. And using this integer, arrive at a contradiction. Now, let's look at this integer real carefully. But first, don't forget to hit the subscribe button, especially if you enjoy watching mathematical proofs, as that's all we do here. Now, if you look carefully at P2, P3, up to Pn, so let me write n equals plus P1, P3, up to Pn, plus dot dot dot, P1, P2, up to P sub n minus 1. Notice this one is missing P1. It has all the prime numbers P1 it has all the product of the n primes, except it doesn't have P1. This one has all the primes except P2. The last one has all the primes except P sub n. See, each one is missing one of them. Okay, so we know that Pi, Pi divides n. Because the prime factorization of n must have at least one of these primes. Pi divides n for some I jammed between 1 and n. That is, one of the prime numbers in here divides Pi, divides n. Okay, now let's look at n slightly differently. We have P2, P3, all the way up to Pn, plus P1, P3, all the way up to Pn. And eventually, we'll get up to P1, P2. This is the one that won't have P sub I. I plus 1 all the way up to P sub n, plus P1 plus dot 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 up to P1 times P2 up to Pn minus 1. Now, let's bracket off this sum, but leaving out this one. This is P2, P3, and just to be clear, no times. Pi is in here. This is P2, P3, up to Pi, up to P sub n. Plus this one, which also has Pi, plus P1, P3, up to P sub I, up to P sub n. Now, just want to do one little thing. Just want to move this further to the left. So, it's this plus this, dot dot dot. Now, you have the one right before. You're going to have P1, P2, you'll have up to P sub I minus 2. You won't have the one you won't have P sub I minus 1, but you'll have P sub I plus 1, all the way up to P sub n. And you'll have the one after this special one. And that one is going to be plus P1, P2, all the way up to P sub I, but we're going to pass I plus 1 up to Pn, plus this last term, which also has the factor P sub I. P sub 1, P sub 2, up to P sub I, up to P sub n minus 1. I will change that one. Well, I have enough room. Plus this one, the one that doesn't have the P sub I. P sub 1, P sub 2, up to P sub I minus 1, times P sub I plus 1, up to P sub n. Now, the nice thing is, from each one of these, each and every one of these, I could pull out P sub I, except for the last one. So we have P sub I times this, P2 up to Pi minus 1 times Pi plus 1, because we pulled out the P all the way up to Pn, plus this one, P1, P3. We remove this one, so we have the one before P sub I, we have the one after P sub I, up to P sub n, plus this one. We factor out P sub I, but we didn't have P sub I minus 1 anyways. So what we have left is this times that. We just pulled out one of them. So we have P sub 1, P sub 2, up to P sub I minus 2 times P sub I plus 1, all the way up to P sub n, plus this one. We have P1, P2, up to the one right before P sub I, which is P sub I minus 1. And then we have the rest, because we pulled out Pi. P sub I plus 2, all the way up to P sub n. The big thing is we factored out P sub I, plus this one. P sub 1, P sub 2, P sub I minus 1, P sub I plus 1, up to P sub n. There never was a Pi in there, so we can factor it out. Now, this is what n equals. And we're saying that Pi must divide Pn. Now, I'm going to call what's in here A. So what we have is the n is equal to P sub I times A plus this. P1, P2, P sub I minus 1, P sub I plus 1, up to Pn. And this is n. Well, P sub I divides n, and P sub I divides P sub I A. That implies that P sub I divides Pn minus P sub Ia. Well, n minus this is that. That implies that P sub I divides P1, P2. It's a prime, and it divides the product of other primes that doesn't contain P sub I. That's not true. If all of these numbers, if all of these n-1 numbers are prime, the only way P sub I will go into it is if one of these n-1 primes were P sub I. But P sub I does not divide P1, P2, Pi minus 1, P sub I plus 1, all the way up to P sub I, P sub n. That's the contradiction. But what are we contradicting? That assume that there are finitely many primes. This contradicts that there are finitely many primes. Hence, there exist infinitely many primes. Yet, once again, we have a proof that shows there's infinitely many primes. If you like watching mathematic videos like this, definitely subscribe to my channel. See you guys in the next video. Watch and learn.